Have you ever tried to push a bicycle from rest? Or had to paddle a boat forward through still water? Hello and welcome back. Today we are exploring something very foundational: what causes an object to move? And more importantly, what keeps it moving? Let's begin with what we all intuitively know: motion requires force. To move a cycle, the rider pushes the pedal. To start a car, the engine burns fuel and generates force. In a horse cart, the horse pulls using its muscular strength. And a boat glides forward only when the oars push the water backward. These are all examples of motion caused by an applied force. It's simple: no push or pull, no motion. But here's the twist: does motion require force to continue? Or only to begin? Let's take a deeper look and travel back to a time before Newton and Galileo. Before Galileo, scientists believed that a continuous force is required to keep an object moving. Their logic seems sound: when you push a cart and then stop, the cart slows down. So they concluded motion needs constant force. But what they missed was this: there's something else quietly working against motion. Friction. The force pushing the object forward is gradually overcome by the frictional force acting in the opposite direction. Once the pushing force stops, friction slows the object to a halt. So it wasn't the absence of applied force that stopped the motion, it was the presence of friction. This misunderstanding led to the belief that force sustains motion. But that belief was about to be challenged. Galileo's experiments changed everything. He rolled balls down inclined planes and observed something remarkable. If friction was minimized, the balls rolled farther before coming to rest. And in a perfectly smooth environment, the ball would keep rolling forever. A ball rolling on a frictionless flat surface would continue moving indefinitely if no opposing force like friction acted on it. Let's think of a real-life example. You're riding a bicycle and stop pedaling. The cycle continues to roll, but gradually slows and stops. Why? Because of friction from the road, the air, and internal components. Now imagine if friction were completely removed, the cycle would never stop. Galileo concluded, no force is needed to maintain motion, only to overcome opposing forces like friction. This became the core of what we now call the law of inertia. And now we arrive at Newton's first law of motion, built upon Galileo's findings. Let me state it clearly. An object continues in its state of rest or of uniform motion in a straight line unless acted upon by an external unbalanced force. That's powerful. Let's unpack it. If a body is at rest, it stays at rest, unless pushed or pulled. If it's moving at a constant velocity, it continues moving, unless a force like friction, resistance, or collision interferes. In short, force is required to change motion, not to preserve it. This law introduces the concept of inertia, the natural resistance of objects to changes in their motion. It's also why this law is sometimes called Galileo's law of inertia. Let's bring inertia to life with a few real-world examples. You're in a moving bus, it suddenly stops. What happens? You lurch forward. Why? Because your body wants to keep moving. That's inertia of motion. Now place a coin on a card over a glass. Flick the card sideways. The coin drops straight down into the glass. Why? The coin resists the change. That's inertia of rest. These moments show us that every object naturally prefers to continue doing what it was doing, resting or moving, unless disturbed by a force. This tendency to resist change in motion or rest is what we call inertia, and Newton's first law explains it completely. Let's solve an example to reinforce the concept. Problem: a toy car is pushed gently on two different surfaces. On a polished floor, it travels 2 meters. On a rough mat, it travels only 1 meter. Why? Step 1. On the polished surface, the friction is low. Less opposing force means the car moves farther. Step 2. On the rough surface, more friction acts against the motion, so the car slows down sooner. Conclusion: In both cases, the car would have kept moving if there were no friction. It stops because of an external opposing force, friction. This proves Newton's first law. Motion continues in a straight line with uniform velocity, unless an unbalanced force acts. Let's quickly summarize what we've learned today. Force is required to start motion, but not to continue it. Before Galileo, people thought constant force was needed to keep objects moving. Galileo showed that in the absence of opposing forces, motion persists. Newton formalized this into the first law of motion, highlighting inertia. Everyday events, like passengers lurching in buses or balls rolling down slopes, all reflect this law. So, to sum up, Newton's first law doesn't just apply to falling apples or bicycles. It governs everything from satellite motion to the way rockets glide in space. I hope you now have a better sense of how forces influence every motion around us. See you in the next session with another fascinating concept of physics.